Hey guys, welcome back. So this is the entropy lecture that we're going to be doing today. We're going to start with our review, just like we always do. And hopefully you guys don't have any questions, comments, issues, problems, whatever. But if you do, please reach out. Email, phone, WebEx, whatever. Let me know what's going on so that we can talk about it. All right, let's get started. And I am sharing my screen. So let's see what's in our entropy lecture. And of course, starting with our review, we're going to calculate the heat of fusion of 1 mole of MgO from O2 and Mg. So I'm looking at this table, and I see MgO solid is negative 601.8. So I'm looking at Mg solid plus O2 gas, and it's going to have to be plus half an O2 gas going to MgO solid. And so we're looking at delta N products minus delta M reactants and so my product at negative 601.8 minus the sum of the number times our that number times how much it takes to make an Mg solid, and of course we can look and see Mg solid is 0. And our O2, again, is its natural state, so the O2 is 0. So that's going to be half of 0 plus 1 times 0, which is, of course, 0. That's equal to negative 601.8. And, of course, that is going to be in kilojoules per mole. We typically report these only as kilojoules and not as per mole, because it's implied that it's per 1 mole that we're making because it's a delta H, not F. So we typically only report that as kilojoules. So there you go. Awesome. Calculate the heat of fusion of NO2 from N2 and O2. So we're talking about NO2. And of course, that one's going to be a gas. And that's going to be made, from N2 gas plus O2 gas to give me NO2. And of course, we'll need a half of an N2 to make that work. So, and this will be a gas. That gas, yep. Okay, so all my stages are on there. So if I look at my NO2 gas, I have NO2 gas right here is 33.85. And then we're going to subtract the 1/2 of the 0 from the N2, which is right there. And then, of course, the O2 gas is 0 as well. And that's equal to 33.85 kilojoules. Okay, that was fun. Calculate the heat of fusion of H2S from H2 and S rhombic. Okay, so we're going to take H2 gas plus S in the rhombic form. And that's going to give me an H2S. And if I'm not mistaken, H2S should be a gas, but let's see what's in here. H2O, H2O, H2O2. Did I actually do this? Looks like I did. So I don't see on this list an H2S. And so it looks like, oh, there it is. H2S gas is right there. Whew, awesome. So that's negative 20.15. It's negative 20.15. And we're going to subtract from that 1 times the H2 formation, which should be 0. And where's my H2, he's over there. Right there, he's 0. And then my S in the rhombic form, which is also 0. So that's negative 20.15 kilojoules. Gee, that was fun. Awesome. Calculate the heat of breakage of the HH bond if H2 is the reactant and 2H gas is the product. So I'm looking at H2 gas. I want to make 2H gas from that. So 2H is my product. So I look over here and I see that H gas is negative is 218.2. So my product's 2 times the 218.2. And then I'm going to subtract 1 times that 0 for the H2, the formation of the H2. And that'll tell me what it takes, the heat of breakage of the HH bond. So in order to make 2 of those H's, that's 2 times that 218.2. So 218.2 times 2, and that gives me 436.4. And I've been doing this for ages, so that value seems very reasonable to me. That is about how much energy it takes to break a hydrogen bond. So that's cool. Awesome. Now we know how that works. So, excuse me, I'm sorry. I swear this only happens when I'm on camera, and I'm so sorry for that. But that's a review of how to work with those standard enthalpies of formation, okay? Now, an ice cube with a mass of 9.53 grams, pressure presumed Ti equals 0 degrees C, is placed into a calorimeter containing 111.24 grams of distilled water at a temperature of 23.2 degrees C. After equilibrium, the final temperature was 15.8 degrees C. Given the following, determine the delta H water, delta H ice, delta H calorimeter, and delta H fusion on gram of ice. Okay, that's a lot, right? Well, so I can see that delta H total is equal to the delta H for the ice plus the delta H for the water plus the delta H of the calorimeter plus the delta H of fusion, and that's equal to 0. The delta H for the water in joules is Cp for H2O times the mass times the delta T. So my mass equals 9.53 grams, and that's for the ice. Ti is going to be 0 degrees C, 273.15 Kelvin. My Tf is going to be, I actually don't need to convert that to Kelvin. Sorry, all of this is in degrees C. Sorry. 15.8 degrees C. And then my mass for the H2O equals 111.24 grams. And the Ti for the H2O equals 23.2 degrees C. Okay, so my water is at 23.2 when I start. That's how much, this 111.24 grams is how much I have. That then gets to 15.8 degrees C. My ice, which is 9.53 grams. Sorry. Starts at 0 degrees C and goes to 15.8. Okay. So my delta H water is the Cp of the H2O. Now, Cp for H2O. And if I look in my exam hands, I have a Cp for H2O that's given. And that's because there's a table of specific heat capacity values that are given. Yank this thing out of here, sorry. So on the bottom of page 10, you'll see specific heat capacities, grams times degrees C at STP. Okay, and I can see from here that the water is 4.18. 4.18 grams per degree C. Okay, so I take that CP for the H2O, the 4.18, multiply that by the mass, 9.5, oh no, wrong mass, 111.24 grams. And then my delta T, so my initial minus my final, the 23, oh, sorry, final minus initial. 15.8 is where I end, minus the 23.2 where I start. And that gives me 4.18 times 111.24 times 15.8 minus 23.2. That gives me negative 3,440. Actually, by the time I run it up, it's 4,1. I can do the same thing to calculate that for ice. And of course, the CP for the ice is actually going to be the same value. So that's that 4.18. We're going to be looking at the mass, 9.53 grams. And my delta T here, final minus initial, 15.8 minus 0, 4.18 times 9.53 times 15.8. That's 629.4. And the delta H for the calorimeter is the CP for the calorimeter times delta T. Now, CP for H2O was given right here. Oops, okay, it's already here. CP for the calorimeter is given right here. So the delta H for the calorimeter, CP of the cal, is 50 joules per degree C. So we multiply that times the change in temperature for that calorimeter. And my change in temperature is going to be my final, that 15.8 minus the initial, which is going to be the temperature of the water that was in it. So the 23.2. And that's negative 370. So if I wanted to calculate the delta H of fusion, that's equal to the delta H of the ice plus delta H of the H2O plus the delta H of the calorimeter. And of course, this side is negative. So one of the sides has to be negative. It's actually going to be the delta H fusion that we move to the other side. But since we want to find that, I'm going to put the negative on the opposite side. Okay, awesome. So negative delta H for the ice, which I calculated to be 629.4. We add the delta H for the H2O, negative 3,441, plus the delta H for the calorimeter, the negative 370, and that gives me 629.4 minus 3,441 minus 370. And then I take the opposite of that because that sign has to change. 3181.6 is what I get. Okay, and of course that's in joules. So if I wanted to put it in kilojoules, I would divide that by 1,000, and that would give me negative 3.18 kilojoules. Cool with that? Awesome possum. All right. Let's see what's next. Questions, comments, problems. Hopefully not. Hopefully you understand that process of how we set that up. So if you do have questions, excuse me, please let me know. I'm going to take a pause here and we will get this set up for our next section in the entropy. And I will talk to you soon. Thanks, guys.